Tell me when.
Go.
Alright. 3, 2,
1. Today on Spud Science, we take a closer look at what really happens when a potato cannon is fired, and we answer the question, what effect does the air pressure in the tank have on the velocity at which the potato leaves the barrel?
Here at Spudside, we have developed a revolutionary potato cannon. It uses a large air tank which can be filled up with a bike pump. When the valve is opened, the air rushes out, propelling the potato projectile to incredible speeds. The tank has a maximum capacity of 150 psi. That's over 149 psi. Initially, we investigated the relationship between pressure and distance, but there was one problem. Do you see the potato here? Yeah, neither did we.
So instead, we decided to get things rolling with our patent-pending Spud board, but the potato was too powerful. So finally, many potatoes later, we came up with this. We used revolutionary synthetic potato technology and the latest advances in potato catching zip lines.
When the potato is launched, it is caught in the tater tube, propelling the tube down the zip line. We can then measure the velocity of the tube and calculate the initial velocity of the projectile, because momentum is conserved according to the law of conservation of momentum.
As always here on Spud Science, we perform regular gravity tests to ensure the gravity is indeed working.
In the first trial, we pumped the air tank up to a respectable 20 psi. That's 20 pounds per square inch. The tater tube has a mass of 2.326 kilograms. The ball had a mass of 0.038 kilograms. The combined mass of the ball and the tube is 2.364 kilograms. Using the always reliable Logger Pro, we calculated that the tater tube was traveling at 0.74 meters per second down the zip line. We then calculated the velocity of the projectile using m1 times v1 equals m2 times v2. According to the law of conservation of momentum, the projectile has to be equal to the combined momentum of the tater tube and the projectile. We calculated that the potato had a velocity of 46 meters per second. That's over 100 miles per hour. We continued this several more times to collect multiple data points. From our data, we made a graph and calculated the line of best fit to determine that the velocity increased by roughly 2 meters per second for every 1 psi. At the highest pressure level, the projectile traveled at 393 miles per hour. As you can see here, there are a few data points which do not fit the line. This can be attributed to a number of different error sources. One possible source of error was that the tater tube oscillated on the zipline after impact. These oscillations caused our calculated velocity for the projectile to be lower because some of the momentum was lost in the oscillations instead of being used for forward momentum. Also, energy was lost due to friction of the pulleys. Another source of error was the loss of the catching mean, which occurred in small amounts during the collision. We did not account for this in our momentum calculations. This concludes another exciting episode of ESPN's Spud Science. Tune in next week to calculate the orbital velocity of our new satellite, Spud.